Okay, this will be the last lesson, Chapter 5, Lesson 5. And what we'll do here is talk about something called enthalpies of formation. Now, we can list the formation of compounds from their elements along with the delta H value under standard conditions. And this is actually listed in the back of our book. Every substance, every compound that we can think of can be thought of as being made from its elements, and then the corresponding delta H can be determined. So these are actually tabulated and placed in the back of our books. So we'll actually analyze this here in a minute. This little symbol, the little knot, this is called the knot symbol, actually refers to standard conditions, which are 1 atmosphere and 25 degrees Celsius. And we want to list all compounds at under the same conditions, because as conditions change, the delta H may fluctuate. And the F here means the compounds are formed from its elements. So this is the same equation we've just seen. What we see here is we got, our compound is C2H5OH. This is actually ethanol, and it contains carbon, hydrogen, and oxygen. So on the left side, on the reactant side, we place carbon, hydrogen, and oxygen in their standard states. Carbon is a solid, hydrogen is a gas, oxygen is a gas. And then we balance the equation so that way our product, our compound, actually has a coefficient of 1. So notice we'll put then fractions as needed, or whole numbers as needed, to make sure this remains a 1. This is important to use fractions. So this shows the formation essentially of 1 mole of ethanol from its elements. And the fascinating or the exciting thing is that we can use these enthalpies of formation now to calculate the delta H's of reactions. This is going to be a different way of calculating the delta H of our reactions. This is going to be a very powerful tool, and essentially it draws on Hess's law. This is if you can actually think of this as a variant of Hess's law, a variation of Hess's law. So if you take a look at this table 5.3, or if you take a look at the appendix in the back of the book, I believe it's Appendix C, what you'll find is a bunch of compounds listed along with their delta H of formation, heats of formation, in kilojoules per mole again. So we actually saw ethanol. We just saw that, and that's listed in the back of the book as negative 277.7 kilojoules per mole. We're actually going to use these values now to determine the delta H's of different reactions. Now, any element, the heat of formation of any element is actually 0. And this is true because an element, it doesn't take any energy to form an element. It is already an element, so therefore we put a 0. So the delta H of formation of nitrogen gas is 0. Same thing with hydrogen, oxygen, any elemental state is 0. So here's the formula we will be using to calculate the heat of reaction, or enthalpy of reaction. And the formula states this: the heat of reaction is equal to this is a sigma, this is a Greek letter sigma, this is the summation of the moles of the heat of formation of the products minus the summation of the moles of the heat of formation of the reactants. Now, this looks like kind of a complicated formula, but if you think of the delta H, if you think of the delta as being final minus initial, kind of like with temperature, final minus initial, it's essentially how much it changed by. In our case, for a chemical reaction, your final is your products, and your initial is your reactants. So think of it that way. Think of it as products minus reactants being final minus initial, and that will help you remember it. We'll also have to make sure we multiply by the moles. If you have 3 moles in the products, we'll have to multiply that delta H by 3, and we'll see that in the following example. So we'll wrap up with this example here. Using the standard enthalpies of formation listed in table 5.3 above, calculate the enthalpy change for the combustion of 1 mole of ethanol. So what we're given here now is a combustion reaction of ethanol. And we can actually determine its delta H from the heat of formations of all these substances. And we'll actually do that on the next page here. So let's go ahead and try this. I will go ahead and let me rewrite the equation that we're looking at. And this will be ethanol, C2H5OH, a very flammable and fun-loving substance. Plus we have 3 oxygens, producing CO2 and H2O, and don't forget to balance the equation. And again, we're looking for the delta H of this reaction. So here is what we're going for. So let's take a look at the back of the book and see if we can find, or let's take a look at the table. And if we don't find it on the table, we'll take a look at the back of the book, see if we can find the heats of formations of all these substances. It looks like the heat of formation, if you take a look at the table, of ethanol is actually negative 277.7. Oxygen's heat of formation, because oxygen is an element, is 0. CO2's, carbon dioxide's, heat of formation is negative 393.5. And water's, if you take a look at that table, I'm going to flip back to the table real quick here. You'll find that water is actually not on here. So since water is not on here, we'll have to consult the back of the book. And for that, I'll show you that how that's done in class. But for the meantime, I've looked up water. Seems to be, the heat of formation of water is negative 285.8 kilojoules. So let's go ahead and sum these up, and we'll use our equation. Remember, our equation is products minus reactants. And we have to make sure we multiply by the coefficients. So our products, I'll go ahead and open a big bracket for the products. So we've got 2 carbon dioxides, so 2 multiplied by negative 393.5, plus we get 3 waters, 3 multiplied by negative 285.8. These are our products, and then it's products minus the reactants. Our reactants are actually, we just have 1 mole of ethanol, which is negative 277.7, and some oxygen whose heat of formation is 0. Now, it's essentially a matter of adding these up. We'll have to keep track of our numbers and our negatives and positives, our signs. So I'll do this step by step. Let me calculate out this portion right here first. So we got 2 multiplied by negative 393.5. That gives us negative 787. Then we're going to add to that 3 multiplied by negative 285.8. And this gives us negative 857.4. So we'll have to combine these values and subtract. Since we're subtracting a negative, that's to be the same thing as adding a positive. So adding 277.7. Let's go ahead and combine these two values then, and 787. That should give us, I believe this gives us negative 1644.4 plus 277.7. And since we essentially had to add 2 negatives, we have a big negative number. So now we'll add to that 277.7 for a total value of negative 1366.7 kilojoules, which is quite a bit, but this makes sense because what we're doing is we're burning ethanol fuel. Ethanol is actually added to car engines, so it should have quite a bit of heat being released. And this essentially is our delta H. For the sake of significant figures, I think we'll keep them all, because when we're adding and subtracting, the least number of decimal places is the rule that follows. So our answer is negative 1366.7 kilojoules. And this is applying Hess's law to a different type of arrangement, where we can use the heats of formation of the substances to give the delta H of any reaction. This is powerful because now if we can write a reaction, we can probably determine its delta H from theoretical considerations, and those will match pretty closely to the actual experiment if we then go on and perform it. Okay, and that will conclude for us Chapter 5, and we will talk a little more about this later.